Hello everyone, welcome to SS Talks Chemistry. I hope you all are doing great. So today we are starting with the previous year questions of the chapter that is your chemical thermodynamics. Okay, and in this from the year 2011 to the year 2025, all the questions you are gonna get of this. Okay, so let us begin with this one. This is the question. So this is from the CSI exam conducted in the June month of the year 2011. The question it says the process is carried out at constant volume and at constant entropy. It will be spontaneous. So you have two of the processes. One is called as the spontaneous processes and other we call that as the non-spontaneous processes. What is the difference between these two? Spontaneous processes are those which continues on their own when no external help you have provided to it. Once you have initiated it, it will continue till its completion. Like flowing of the water from top to bottom, if you consider, it continues on its own. Right. Whereas non-spontaneous processes, if we talk about this, these processes are the one which requires an external help. Like if you want to fill your tanks that is placed at the rooftop, right? For that, what we do is we switch on our motors, right? So the tank it starts filling. As soon as I switch off my motors, the water it will stop filling into that tanks. Right, this is what is happening. So this is the difference between the non-spontaneous and the spontaneous processes, which implies non-spontaneous processes it will stop if the external help we stop it at that point. Right. More example of non-spontaneous you can see in the electrolytic cells and the spontaneous in the galvanic cells. Right. Now in thermodynamics, to look upon to the spontaneity of the reactions, we make use of the Maxwell square. That looks like this. These arrows they are pointed. It is good people have studied under very amazing teacher. This is what we are having. Right. So now they have asked at the constant volume and at the constant entropy. So here the energy terms that you are having, be it your Gibbs free energy or the Helmholtz free energy or the internal energy or the enthalpy. If these are four of these you are having, they are gonna be less than zero. But here the constant values in all of the four it differs. If I talk about the terms of the Gibbs free energy, so we say that delta G value it is gonna be less than the zero provided the temperature and the pressure, that is the variables which are present on its sides it is kept to be the constant, right? Similarly in terms of the Helmholtz free energy if I'm talking about, so this is gonna be less than the zero if the condition is that on the sides the variables are volume and the temperature they are kept to be the constant, right? Similarly in terms of the enthalpy if we talk about, there the side variables are pressure and the entropy. This is gonna be less than zero if these two are kept to be the constant, right? Similarly in terms of the internal energy now, here the side variables we have, that is S and the V, it is less than the 0. Now from our given conditions, if you see the constant volume and constant entropy, so that is, it is in the case of the internal energy we are having this. Right, so that means delta U it will be less than 0 for the spontaneity conditions at constant volume and at constant entropy. This is in terms of the energy that we write it. Right, but in terms of these variables also you can write this thing. So in the terms of these variables, suppose the volume term if I'm taking, so here we will say that delta V, that is, now go on the sides, you have the Helmholtz free energy and the temperature. So A and the T, this should be less than the 0, right? And the similarly on the opposite other side of it, it is having the internal energy and the entropy. So delta V at the constant internal energy, this is the volume, this is internal energy and the entropy it is less than 0. This is how we write it. Similarly for the temperature also, that is placed in the below side. So here on the temperature side, this Helmholtz free energy and the volume it will be taken delta T and the at constant A and at constant V it should be less than 0 and the delta T at the constant G and the P it should be less than the 0. So how you can remember this? The ones which are placed in the below side in this square that we have drawn, that is this volume and temperature, this is gonna be less than 0. Whereas in terms of this entropy and the pressure, if we are looking, so that is gonna be more than zero. So delta S, it is greater than the zero if the, now go on the sides, if the enthalpy and the pressure is kept to be the constant. Similarly, on the other side of the entropy, you are having the internal energy and the volume. So delta S at the constant internal energy and the volume, it should be greater than the zero. Similarly, for the pressure, you will be writing del P at the constant G and T, it will be greater than the zero, and the del P at the constant of the enthalpy and the entropy, it will be greater than zero. See, these all are the conditions which is in terms of the variables and the energies at different constant variables or the different energy and the variable values. These are gonna be uh, implementing our spontaneity conditions. Okay, so this is the whole concept of it. Right, now let us move on to the next question. This is the one. So the question, it says that the variation of an equilibrium constant K of a certain reaction with the temperature, it is shown like this. So this expression has been given to us. R value has been given. So what is the value of the delta H naught and the delta S naught in this? So now here you see that ln of the K, it is given to us. Ln of the K, 3 plus of 2 into 10 raised to the power of 4 upon the T we are having. Right now we know we have to correlate this natural logarithmic of the K, that is equilibrium constant, with the enthalpy value. That you can get it in the Van 't Hoff equation. It is in the Van 't Hoff equation. In the Van 't Hoff equation, we know that d of the ln of the K by the dt, this is equal to delta H upon the RT square. This is the expression. Now take the dt on the other side. You will be getting d ln of K, that is equal to delta H upon the RT square into the dt of it. This is what we will be getting. Now you can see here the ln of the K, it is there. So what you do is you integrate on both the sides. Integrate on both the sides, we will be getting d ln of K, this is equal to delta H upon the R into the integration of 1 by T square into the dt of it. On solving this, we will be getting that ln of the K, this is equal to delta H upon the R. Now, integration of the 1 by T square, this is gonna be minus of the 1 by T. Now, integration we have done without the limits. So, a constant value, it will be added in this. Okay, so it becomes minus of the delta H upon the RT plus of the C. This is equal to your ln of the. Now, the given expression that we were having, this was equation 1, you can say, and this is equation 2 you are having. So you can equate both of this because both of this are the ln K values only. From on comparing 1 and the 2, 1 and the 2, we are getting that the C value, it is 3 in this case, and the delta H upon the R, which is with the negative sign, this value is equal to 2 into 10 to the power of 4 of it. Right? So from here, delta H value, it could be calculated. Delta H is minus of 2 into 10 to the power of 4 into the R value. So it becomes minus of the 2 into 10 to the power of the 4 into the 8.314 joules per mole per cal. So this is the value that we are getting, right? So on solving this, the value you will be getting, that is minus of 16.618 into 10 to the power of 4. This is in the units of this joule per mole. You will be getting this. This is in the units of joule per mole. Now in the kilojoule, the value they have asked it. So divided with the factor of the 1000. So it will become minus of 166.18 kilojoule per mole of it. So this is gonna be the value of the delta H in this. Okay. So from this only, try to eliminate the options. So we are having the value of minus of the 166. From this you can see option A and the option B, it can be eliminated, right? So that means answer is gonna be from the C and the D only. Now you can see the magnitude, it is already the same for the other thing, that is delta S naught. Only the difference in the sign it is there. Right. So let us try to find that delta S naught now. S naught, it means at the standard conditions we have to find it. That means temperature we have to keep at 298 Kelvin in this. Right now we know that delta G value, it is delta H minus of the T delta S of it. Right. Also we know that delta G, it is equal to, now at the standard conditions it is there, so not you can apply it over here. Now delta G, it is minus of the RT ln of the K. Now both of these expressions of the delta G not only it is there, so can be equated. So it will be minus of the RT ln of the K, that is equal to delta H naught minus of the T delta S naught of it. From this T delta S naught, this will be delta H naught plus of the RT ln of the K. Right. So from here delta S naught, it is equal to delta H naught plus of the RT ln of the K upon the temperature. Right. So now all these values are known to us. We just have to substitute their values. So it will become 1 by dt into, now minus of the 166.18, this is in the units of kilojoules per mole we have calculated, plus of 8.314 joule per mole per Kelvin into the temperature, keep it as 298 Kelvin. So it becomes in the units of joule per mole. Right. Into the ln of the K. Ln of the K value, it's already given to us, which is this one. So substitute that. So I'll be multiplying it with the factor of 3 plus of 2 into 10 to the power of 4 upon the temperature, 10 to the power of 4 upon the temperature, which is your 298 Kelvins in this. Right. So just solve this. Here also this temperature value you can keep it. That is gonna be 298. 298 Kelvins. So this is the one we are getting. So on solving this, we are getting that minus of 557.65 plus of 589, 582.92. Okay. On solving this you can see it is coming out to be a positive value, that is 25.278 in the units of joule per mole per Kelvin. So this is what we are getting. So here you can see the sign, that is of the positive value we have got it, that is in the option C, it has been given to us. Right. So C will be the right answer in this case. Okay. Now moving upon to the next one. In this question it is given the chemical potential of a component 1 in a solution of a binary mixture. It is given by this: mu is equal to mu naught 1 plus RT ln of Pt, where Pn is the partial pressure of the component 1 of the vapor phase. The standard state, that is of the mu 1 naught, it is dependent upon which of the following, that is it is dependent upon temperature or pressure, or only on the temperature. So mu1, it is equal to mu1 naught plus the RT ln of the P1. This is what it is given. So what basically is the chemical potential? Chemical potential, it is just a change in the thermodynamic functions that you get on addition of some amount of the substance to it. That is in the open system, this property it arises, right? So now this mu1 naught that you are having, it is dependent both on the temperature and the pressure. It is dependent both on the temperature and the pressure. Whereas the mu1 naught, that is at the standard conditions that you are having, it is dependent upon the temperature only. It is dependent on the temperature only. It is not dependent upon the pressure conditions. Okay. So now about the mu1 naught you have been asked. So it is depends on the temperature only. Option C will be the right answer in this. Okay. Next, this question now. So here for a system of a constant composition, the pressure is given by. Again using your Maxwell square, you can do this. This is the one. Good people have studied under very amazing teacher. So here we have to find the value of the pressure now. So here we know that du value that you have, so du that you are having, it is dependent upon the dV and it is dependent upon the entropy. Now opposite of the volume you are having the pressure and the arrow from the pressure it is going away from it. So minus of the PdV, and for the ds opposite of this we are having is the temperature. The arrow is going towards it, so it is gonna be plus of the TdS. So now you can see at the constant volume, if I see it at constant volume, so dV value it will become 0. So from here you will be getting del U by the del S. This is at the constant volume. This is equal to my temperature. So this is the temperature. Now if I talk about at the constant entropy, at the constant entropy if I see, so in that case ds will be equal to 0, right? So del u by the del v at the constant of the entropy, this is equal to the minus of the pressure. So this is the expression that is giving us the value of the pressure, right? So from this, pressure is minus of the del u by the del u by the del v at constant of entropy. This is the one. Option B is the right answer in this, right? Now moving upon to the next question. This one it is there. So for a reaction, it is given what is the value of the delta U minus delta H minus of the delta U in terms of the kilojoules at a 300 Kelvin temperature and at 1 bar pressure. So now we know that delta H it is equal to delta U plus of the P delta V of it. Now for a chemical reactions, for the chemical reactions, this value that is delta H it is equal to delta U plus of the delta Mg into the RT of it. This is the expression that we use for the chemical reactions. Now here delta Mg it is changed in the number of the gaseous moles that we have. So delta Mg we define it as the number of the gaseous moles. Delta Mg is number of the gaseous moles on the product side, gaseous moles on the product side minus of the number of the gaseous moles, number of the gaseous moles of the reactants. This is how we define it. Now in the given reaction here you see the on the product side you are having two gaseous moles, so that means delta Mg here it is gonna be 2 minus of. Now on the reactant side we are having 3 plus of the 1, that is 4. So 2 minus 4, that is it is minus of the 2 we are having, right? So from here if I see delta H it is equal to delta U plus of the. Now delta Mg it is minus of the 2 into the RT of it. This is what we are getting. Now the differences of the delta H and the delta U. So delta H minus of the delta U, this is equal to minus of the 2 RT of it. So here we are having minus of the 2 into the R value, which is 8.314 joules per mole per Kelvin into the. Now the temperature it has given to us at 300 Kelvins. So this is at 300 Kelvin. So units Kelvin per Kelvin get cancelled. It is in the joules per mole. We have been asked to find in the units of the kilojoules. Right. So here this mole term that was involved over here, mole and per mole it will also get cancelled. So this you are getting in the units of the joules. Right. So on solving this, and to get it into the kilojoules divided with the factor of the 1000, so it will come out to be as minus of 4.9 kilojoules of it, or it is approximately minus of the 5 kilojoules. So this is gonna be my answer in this case. That implies option A is the correct answer in this case. Okay, moving upon to the next one. This question, 1 mole of the CO2, we are having 1 mole of the CO2 and 1 mole of the N2 you are having, and the 2 moles of the O2 it is that they were mixed. What is the entropy of the mixing? So delta S of the mixing, this is equal to minus of the R summation of the Ni into the ln of the Xi of it. This is how we find it. So now here it is minus of the R. Now N of the oxygen into the ln of the X of the O2. X is the mole fraction and Ni is the number of the moles of it. So this is CO2 firstly. So that let us write it in the same order. Number of the moles of the CO2 into the ln of the CO2 plus of. Now here again, number of the moles of the N2 into the ln of the mole fraction of this N2 plus of the number of the moles of the O2 into the ln of the mole fraction of this O2. Right? This is gonna be there. So this is minus of the R. Now number of the moles of the N2 this CO2 we are having, that is 1 into the ln of the 1 upon the 4 it will be there, plus of the 1 into the ln of the 1 by 4 plus of the 2 into the ln of the 1 by 2 by the 4 it is there. This values we are getting. So on solving this, it becomes minus of the R into the 2 times ln of the 1 by 4 plus of the 2 times ln of the 1 by 2 of it. This we are getting. So now just simplify this, minus of the R into the 2 times ln of the 1 by 4 plus of the 2 times ln of the 1 by 2 it was there. So now we can write it as minus of the 2 ln of the 4 and the minus of the 2 ln of the 2. Write this, we can write it. This is minus of the R. Negative sign you can take it outside. So negative will become positive. So it becomes 2 times ln of the 4 plus of the 2 times ln of the 2. So now this 4 ln 4 that I am having, this 2 can be expressed in the terms of the ln of the 2. So it becomes 2 times ln of the 2 raised to the power of 2 plus of the 2 times ln of the 2. So this is the R. Now this in the power, it can come in the front. So it will become 4 times ln of V2 plus of the 2 times ln of V2 into the R. This is equal to 6 ln of V2 into the 6R ln of V2. This is entropy of the mixing that we are having. Okay. So this is gonna be my answer. That is, the correct answer is the option A in this case. Right. Next, this question now. For a liquid vapor equilibrium of a substance dP by the dt at 1 bar pressure and at 400 Kelvin, it is this much. So dP by the dt value, this is given to us, which is 8 into 10 to the power of minus of 3, that is bar per Kelvin. The temperature we have been given, that is 400 Kelvin, and the pressure is given as to be 1 bar. And if the molar volume of the vapor, so volume of the vapor it is given, that is 200 liter per mole of it. The molar volume of the liquid is negligible. The molar enthalpy of the vaporization. Now dP by the dt, from the Clausius-Clapeyron equation we are having, Clausius-Clapeyron equation, we have that dP by the dt, that is for the phase transition processes where the solid liquid is in equilibrium with the vapors. This is the one. So dP by the dt, it is equal to delta H upon the T delta V of it. Right. So now here delta H upon the T. Now here delta V, change in the volume of the vapor phase minus the volume which is of the liquid phase we are having. So this is equal to your dP upon the dt of it. Okay. So now all the conditions have been given to us. We just have to substitute the values and find the value of the delta H in this. So 8 into 10 raised to the power of minus of 3 in the units of bar per Kelvin. This is equal to delta H upon the temperature which is given to us as 400 Kelvin 400 Kelvin into the volume of the vapor, which is 200 liters per mole of it. For the vapor, liquid phase it was 0, so that we are neglecting it. So from here delta H, it is 8 into 10 raised to the power of minus of 3 bar per Kelvin into the 400 into the Kelvin into the 200, which is liter per mole. This is what we are getting, right? So now here the units you see per Kelvin and this Kelvin term it will get cancelled out. So here the answer we are getting, that is in the liter bar per mole we are getting, right? So it is coming out to be as 8 4s are 32, 32 2s are is 64 into 10 to the power of minus of 3 into 10 to the power of 4 of it. So it is becoming 640, that is in the units of liter bar per mole. This is what the units we are getting. The answer we have been asked in the units of kilojoules per mole of it. Right. So for that unit conversion you have to make it. So now we know that it is multiply this with the 8.314 in the units of joule per mole per Kelvin of it, divided with the one which is in the liter bar per mole per Kelvin, that is 0.08314 liter bar per mole per Kelvin. So from here if I see the common units which are getting being cancelled. So liter bar and liter bar is getting being cancelled. Per mole and per mole it is getting being cancelled out. This per Kelvin and per Kelvin term it is getting being cancelled out. This comes out to be as approximately 100 over here, right? So it is becoming 64,000. This is in the units of joule per mole, right? Now we want it in the units of kilojoules per mole, so it will be 64 kilojoules per mole of it. This is gonna be the answer, right? So the unit conversion was important in this. So 64 kilojoules per mole, that is option B, it is becoming the right answer in this. Okay, next this question now. For a reaction which is given to us, that is water plus the carbon. So water here is in the gaseous phase with the carbon. This is in equilibrium with the CO, that is in the gaseous phase, plus the water which is in the gaseous phase. Right. For this process, the variation of the energy parameters, which is your Gibbs free energy, the enthalpy and the T delta S not for the reaction over the large temperature range, it has been shown to us. So A, B, C have been given to us. We have to show that A, B, C, it represents which of the energy parameters in this. Okay. So firstly here you see about the entropy if I see. Here the number of the gaseous moles on the product side it has increased now. Here two gaseous moles these are present and here it was only one gaseous mole we were having it. So entropy, which is degree of the randomness of the system, it is increasing in this case, that means it is positive. Right. So that means T delta S if I see it with the increase in the temperature, now T delta S value it is positive. Like multiplying this with the temperature and that too with the increasing temperature, overall value it's gonna increase with the increase of temperature. With the increase of temperature. Right? This is what we will be seeing it. So here it's the from the given plots if I see, it is the A that you are seeing that with the increase of the temperature, the energy value it is increasing in this. Right. That means P delta S, it is represented by the A plot. Right. From the options if you see, here it is saying that A is representing delta G naught, incorrect. C it is saying A is representing delta G naught, again the incorrect. A is representing delta, it's not, again the incorrect. In this option only you can see A is represented by P delta S naught. So D is gonna be the right answer. But let's check the other options also. Delta G value we know it is delta H minus of the T delta S of it, right? So now here this value it is positive. This we have seen it. So as the temperature it will increase. As the temperature it will increase, keep enthalpy for the while to be the constant. You will be seeing the term which is in the negative. Its value it is increasing, which implies delta G value it's gonna decrease, right? So as the temperature it increases, delta G it decreases with the temperature, right? So this is shown in the plot, that is the C option. It is showing that as the temperature it is increasing, the energy parameter it is decreasing in this. That means C is representing your delta G value. Okay. So here in the option B only you can see C is representing that this is delta G naught. So option D, it obviously becomes the right answer. Okay, next this question now. An ideal gas, it was subjected to a reversible process. It means the one which we carry out very slowly. So here is suppose this beaker you are having is containing the gaseous modes and this piston has been placed over it. So you have to apply the weights over it. So what you are doing is instead of applying keeping a large weight over it, you are placing the small pebbles over it. At a time, you are bringing one pebble and placing over it, right? So by slowly this process you are taking it to the final level, that is this one. Suppose the piston it has gone to this level. So initial volume it was V1 and this is the final volume V2. So now slowly we are keeping this pebbles. So due to that, what is gonna happen? If this pebble that you have placed, due to that the piston it will be moving to a smaller extent only, right? That means if I remove this pebble also, this piston it can come back to its original position also. That means it is reversible in the nature. This is what is meant by the reversible conditions, right? An ideal gas was subjected to a reversible adiabatic. It means that the Q value it is zero. No heat is observed in this process. The expansion process it is taking, and then it is coming to the initial volume was restored by a reversible isothermal compression. So here what is being done, if I see the pressure volume plot in this pressure volume plot, initially you are having these gaseous molecules which is at the point A, suppose it is there. It is subjected to reversible adiabatic expansion. Expansion means the volume in this it is increasing. So this is the initial volume V1. This is going to the volume with that is V2. So this is the point B it is going. So it is the adiabatic. So this type of the plot we can see in this. And then it is coming back to the initial volume was restored by the reversible isothermal compression. So here it is adiabatic and the reversible process. Now it is restored. So it is going back to the position A, that is this one, like this. It is going. So here you can see it has gone to the initial position because the volume in this it is gonna be the same only. So this position it has returned back through a different process which is your isothermal compression. Isothermal compression it is being done in this. Right. So this is what is being shown over here. So now if Q it denotes the heat which is added to the system, then the work and W is the work done by the system. Then the which of these processes it is gonna be true. That means work is being done on the system or it is by the system, that is, or the work done it is positive or the negative we are having. So you can see you are going from A to B and then you are returning from B to the A process you are returning. This is what is happening. So you can see we are going in the anti-clockwise direction. We are going in the anti-clockwise direction we are going. Now the work done we are shown by the area under the curve. Area under the PV curve. This is what the work it is being shown. Now in the anti-clockwise direction, the work done it is taken to be the positive. If it is in the clockwise direction, then it is taken to be the negative. That means here the W that we will be having, this is gonna be greater than the zero. Okay. Now the first process it was reversible adiabatic. That means Q in this it was zero. Right. The second process it is isothermal compression. Now in the Carnot cycle we have learned, in the Carnot cycle you have learned that for the isothermal expansion heat is given to the system, but during the isothermal compression the heat is given by the system. So this is gonna give the heat. That means Q it is negative in this case, right? So Q value it is gonna be less than the 0. W is greater than 0 and Q is less than the 0. This is what is happening in this process. Q is greater than the 0 and Q is less than the 0. W is greater than 0 and Q is less than 0. Option B will be the right answer in this. I hope the concept it is clear. Okay. Now the next this question we are having. Indicate which of the following relations it is not the correct one. Okay. So again with the help of the Maxwell square we can do this. We are having this plot which is good people have studied under very amazing teachers. Right. So the first variation is for del P by the del V. So del P by the del V. So del T by the del V. Now opposite of the temperature you are having this entropy and the arrow is going away from it. So a negative sign it will be placed. This is equal to del P by the del S, del P by the del S. Now opposite of the pressure you are having this volume term and the arrow is going towards it. So here it is gonna be this one. So from this option if you see the option A it is the accurate expression that has been given to us. Right. Next one if I see the B1 that is for the del T by the del P. Del T by the del P. So this way we are going del T and the del P. Opposite of the temperature it is the entropy value. The arrow is going away from it so a negative sign it will be placed. This is equal to now del T by the del P it is equal to del V by the del S, del V by the del S. The opposite of the volume you are having the pressure term. Again an arrow is going away from the pressure so a negative sign it will be placed in front of it. So you can see these negative signs on both the sides it will be cancelled. So that means here it is showing that a negative sign is placed in this expression. This is the incorrect one. So we were to choose the incorrect only. Option B will be the right answer. Rest also options you can check it. The C1 that is there, it is for the del S by the del V. So del S by the del V, opposite of the entropy is this temperature term. So this is the arrow is going towards the temperature, so positive sign it will be there. This is equal to del P by the del P by the del P at the constant of the volume. Right? So this is the arrow is going towards it. So again the positive sign it will be placed here also the negative sign it has been placed. So some misconception is there in the options. This also is the incorrect one. Here negative sign it will be not placed. So answer is either B or the C it will be there. Okay. The option D you can also check it. That is for the del S by the del P. Del S by the del P. Now this is at the constant temperature. A positive sign it will be there. This is equal to del V del S by the del P we were seeing, so it is del V by the del T. Now opposite of the volume is the pressure term. The arrow is going away from it, so negative sign it will be placed in front of it. This is the what we are getting. So option D that is shown to us. This is the correct one. So I either the answer it's gonna be B or the C it will be there. Okay. Next, this question now. For the water, delta H of the vaporization has been given to us. The molar entropy of the vaporization that is gonna be there. So water is evaporating. That is from liquid you are going on to the vapor phase. For the phase transition, the entropy value that you have, this is equal to delta H of the vaporization upon the temperature which is its boiling temperature that we have. Delta H of the vaporization is 41 kilojoules. So 41 into 10 raised to the power of 3 joule per mole we are having. Right. Upon the temperature is the water it is boiling. Water boils at 100 degrees centigrade, that is at 373 Kelvin. So just solve this. You will be getting the value as 110 kilo. This is in the joules per mole, per Kelvin. This is what the value we will be getting. So that implies 110 joules per mole per Kelvin. Option B is the right answer in this. Okay. Next, this question now. So this question it says a car not takes up that is 90 joules of the heat from the source which is kept at 300 kelvins. So temperature of the hot body we are having which is 300 kelvins and the amount of the heat which is being observed it is 90 joules of it. The correct statement among the following is it transfers this much heat to the site. Okay. So here this temperature and the heat which is being observed or it is ejected, it can be correlated with the relationships of the efficiency Efficiency of the Carnot heat engine, it is TH minus of the TC upon the TH of it. This is in terms of temperature. This is equal to QH minus of the QC upon the QH of it. Right? So this is equal to 1 minus of TC upon the TH, or the 1 minus of the QC upon the QH of it. Or we can say TC upon the TH. This is equal to QC upon the QH of it. Right. Now from the options, if you see, left hand side you have to equate it to your right hand side. This condition it should be satisfied because both these are the efficiency values only. So now we have been, first option it says it transfers this much 60 joules of heat to the sink, which is at temperature 200 Kelvin. So temperature of cold body, if I see, that is 200 Kelvins, and the QC value if I take 60 joules. So this ratio if I see, TC upon the TH, this value it is equal to 200 upon the 300. That means the ratio value it is 2 upon the 3. Right. Similarly, the QC upon the QH value, this is 60 upon the QH, which is 90. So you can see the ratio is again coming out to be as 2 by 3 OT. So we can see that left hand side is being equated to the right hand side, which implies that this option is only gonna be the correct answer. Rest options also you can check it, you will be not getting this particular scenario. Okay, so A is the right answer in this case. Moving upon to our next question now, that is this one. The internal pressure for a real gas, it is related to its compressibility factor, which is PV upon the RT, by which of the following expressions. So internal pressure, which is del U by the del V at constant temperature, from the first thermodynamic equation of the state we can solve it. First thermodynamic dynamic equation of the state we are having, according to which my del U by the del V at the constant temperature, this is equal to temperature. Now this tells us about the pressure values. So this is del P by the del T at the constant of the volume. Now this has the units of the pressure only. So pressure only it can be subtracted from this. This is the value that you get. You can even derive this from your Maxwell square using the du value, then differentiating that complete expression with the volume, you will be getting this final expression only. Right. Now for the while Z value it is PV upon the RT, or the pressure value it is ZRT upon the V of it. We need is del P by the del T at the constant of the volume. So del P by the del T at the constant of the volume, it is del by the del T of the ZRT upon the V of it. This differentiation we have to do it at the constant of the volume. So now that means the this Z that I am having, this could be the function of temperature, but we cannot take it outside. So the constant values for the while it becomes the R and the V. So these are coming outside. So we are having del by del T. Differentiation of this we have to do it at the constant of the volume. So apply the product rule over this. So it will be R by the V. Keeping the first function as it is, differentiation of the second. So del by del T of the temperature T only, it will be unity plus of T. Now temperature keep it as it is, second function as it is. Differentiation of the first, which is del Z by the del T as the constant of the volume. This is gonna be the value of the del P by the del T at the constant of the volume. Substitute this in the given expression. So del U by the del V at the constant of temperature, it will be temperature into the R by the V, this value that we have got it, the Z plus of the T into the del Z by the del T at the constant of the volume minus of the T value. This thing we will be getting. Open the back brackets now. So it becomes ZRT upon the V plus of the RT square upon the V into the del Z by the del T at the constant of the volume minus the pressure. So now this expression it was there, that Z is equal to PV upon the RT. From here pressure you got it as ZRT upon the V only. That means this value ZRT upon the P, this is nothing but your pressure only, plus of the RT square upon the V into the del Z upon the del T at the constant of the volume minus of the pressure. So this plus pressure term and this negative pressure term, it will get cancelled out. So that means internal pressure, it is equal to RT square upon the V into the del Z by the del T at the constant of the volume. This is what the internal pressure it is correlated. Okay. This is your final expression. From this, the options, if you see, del U by the del V at the constant of temperature, it is RT square upon the V into the del Z by the del T at constant volume. Option C is the right answer. Okay. Next, this question now. Which of the following statement is true for a cyclic process? Now, what is meant by the cyclic processes? Suppose you are starting a process from this particular point, you are following a certain path you are obeying, like this the path is obeyed, and you are coming back to the initial position only. This is the final and the initial position you are coming. That means you started from some point coming back to the previous one only. That means if the state functions, if we talk about state functions, that is independent of the nature of the path, independent of the nature of the path, nature of the path. For them the change in the state functions, if you see like del u du or the del u you are observing, or the change in the entropy or the change in the Gibbs free energy, these values they are gonna be zero. This is true only for the state functions. But for the path functions, if I talk about, for the path functions, that is, they are dependent upon the nature of the path that have been followed. The example is work, heat, and the heat capacity, heat and the heat capacity. All these three are the path functions, rest all are the state functions. For the path functions, this value which is change in the internal energy, be it partially or the complete change, it is not equal to the zero. Right? So from the given options now I see which one of the following it is the true one. So here del q is equal to 0 it is given. That is not possible because q is your path function, not the state function. Had it been some state function, then we could write it, right? Similarly, the work done that it is given, again, it is your path function. For this statement, it is also not the true one, right? So this is also the incorrect. Next, heat can be completely converted into the work, and the B statement that says work can be completely converted into the work. So here this relationship we have between the work and the heat, all the work that you are having, it can be converted into the heat 100%. This is possible, but all the heat is cannot be converted into the work 100%. Some of the heat is lost to the environment. Okay, so work can be completely converted into the heat. The statement is the true one. Heat is completely converted into the work, incorrect. Okay, so B is gonna be the right answer in this. Next, this question now, the correct thermodynamic relationships among the given is. So for the pressure term, again this is being asked. So you are seeing this question, it has been repeatedly asked. So here the first question or the second question only it was there. In 2011 also the question related to the pressure it was being asked was. This was the question. So here you see the direct pressure value it was asked. Now here the relationships has been given to us, which is asked to find the value of this correlating to the minus of the pressure. So again using your thermodynamic square, good people have studied under very amazing teachers, right? So we can see du value that you are having. This is dependent upon the volume term and it is dependent upon the entropy. Now for the volume, opposite of it, it is the pressure. Arrow is going away from it. So minus of the P plus of the TDS, it will be there. So at the constant entropy, if I see at the constant entropy, we will be getting that ds value it will become equal to the 0. So du it will be equal to minus of the PdV or del U by the del V at the constant of entropy. This is minus of the pressure. So del U by the del V at the constant of the entropy. This is minus of the pressure. Option A, it becomes the right answer in this. Okay. Next, this one now. The heat capacity for the 10 moles of the ideal gas, that means N value it is 10 moles at a certain temperature, it is 300 joules per Kelvin at the constant pressure. So Cp value it is given to us, which is 300 joules per Kelvin. The heat capacity of the same gas at the same temperature but at the constant volume, Cv is being asked to us. Now for the ideal gases, for the ideal gas Cp minus Cv, it is equal to the Nr, right? So from here Cv value, this is gonna be Cp minus of the Nr of it. Cp value it is 300 joules per Kelvin. Now here minus of the Nr we have to do it. So number of the moles it is already given to us, so that we can substitute. So it will be minus of the 10 into the minus of the 10, which is in the moles we are having, into the 8.314 joules per mole per Kelvin. So from here this per mole and mole term it will get cancelled. Units it will be joule per Kelvin. Same units can be added or subtracted only. So this is 300 minus of 80.314 in the units of joule per Kelvin. We will be getting the value which is 216.86. This is joules per Kelvin. This is the value of the Cv that we will be getting. Alright. So this is approximately equal to the 217 in the units of joules per Kelvin. That is option B is the right answer in this case. Okay. Next. This one now, the Maxwell relation derived from this equation, which is dg it is equal to v dt minus of the s dt of it. So in this dg we know delta g that we have, it is your state function. It is my state function. So this follows the Euler's theorem. Euler's theorem it is followed in this. What is the Euler's theorem? Let us firstly learn about this. If you have a z value which is function of this x and the y in this, so the exact differential for this it can exist because of this being a state function. So dz in this case, this is equal to del z by the del x at the constant of the y into the dx, a plus of the del z upon the del of the y at the constant of the x into the dy of it. This you can replace it with the m and the n values. So this complete differential dz it is equal to m dx plus of the n dy of it. This is how we can write it. This is my dz. This is how we can write it. If the Euler's theorem is being obeyed in this case, so you take this del m with the differentiation with this the other, which is del of the y, keeping the x to be the constant. This thing is equal to del n by the del of the x at the constant of the y. This is what it is, what this Euler's theorem it states to us, and you have to apply the same thing to the given equation, which is of the dg. Now dg it is equal to v dt minus of the s dt of it. Now instead of the m you are having this v value, and this is the n value which is the entropy minus of the n which is there, which is the n value in this, right? So that means del v by the del t at the constant of the pressure. So this is m dx minus of the n into the dy of it. This is what this expression is given. So m value it is v and differentiated with the dy, that is the del t in this at the constant of the pressure. This is equal to minus of the del s by the del t that is at the constant of the temperature. This is what this expression is gonna be there. Okay, I hope the complete concept it is there. So del V by the del T at constant of pressure, it is minus of the del S by the del P, minus of the del S by the del P at the constant of the temperature. That means the option C is the right answer in this. Okay, next this question now. The chemical potential of the ith component it is defined as. So chemical potential, this term you encounter in your open system. This is nothing new. Just in the open system, what we consider that some number of the moles are also considered in this. So if G you consider, it is considered as a function of the temperature and pressure. This is for the closed system. From the Maxwell square, you can see that G is function of the this temperature and the pressure. Good people have studied under very amazing teacher. So G you can see it is function of the temperature and the pressure. But now along with this, the number of the moles are also considered, which is Ni or the Nj component of this, which basically describes that how what is gonna be the change in this Gibbs free energy value if the ith component it has been added into it. That is chemical potential it is del G by the del of the Ni, keeping the next things to be the constant, which is temperature, pressure, and the other components of the gas that you have added to, component that you have added to it. Right? So this is are the conditions which are constant that is important in this. For the Gibbs free energy term, if we are talking here, the temperature and pressure is kept to be the constant. Similarly, now, in terms of the another and other energies, also we can write the chemical potentials. That is nothing, just it is describing that how is gonna be the thermodynamic potentials or the functions it is gonna change if we are adding some component in this. Okay, so here, if in terms of the enthalpy, if I'm talking, so here it will be constant at the at the constant entropy and at the constant pressure. That means this mu I it is also equal to the del H upon the del of the Ni at the constant of the entropy and at the constant of the pressure. Okay. Similarly, in terms of the internal energy, also I can write it, which is gonna be del U by the del of the Ni. The constant things now it's gonna be entropy and this volume term. These two things that will be constant, and this is gonna be equal to, in terms of the Helmholtz energy, I can also apply it del A by the del of the Ni. This is at the constant volume and at the constant temperature. So all these equations in the Gibbs free energy, it is del G by the del of the Ni at the constant of the temperature and the pressure. The only difference that is arising is of the constant variables that we are keeping. Right. So now just look for that only. So chemical potential is del U by the del of the Ni, that is at constant temperature and the pressure. This is the incorrect. In this way you could write it if you are talking at the constant entropy and at the constant volume. Right. So del H at the constant temperature and pressure, again the incorrect. A in terms of the temperature and pressure, again the incorrect. Dg in terms of the constant temperature and pressure, this is the correct one. Okay. Next, this question now. This question it says the work involved in the isothermal reversible expansion from the volume Vi to the final volume of an ideal gas it is given by. So now we know it is the isothermal, which means the temperature is kept to be the constant, and we are having a reversible process. That means the one which is carried out slowly, that I have already seen. Reversible processes, in this the P external value it is not constant. It is not constant. How we are saying? Suppose this is the piston that you are having. Applying the small pressures over it, you are bringing it to the final volume, that is V final. This is the final volume you are bringing it to this particular positions. Now here the pressure you are applying small times you are applying it. That means at any point of time the external pressure is not the constant. Right. Now the work done it is minus of the P external into the dV of it. Right. Integrating this. Now here P external we can write it as nRT upon the V of it into the dV of it. Now nRT, because N is the number of moles which is gonna be the constant, T is the temperature which is the isothermal conditions, so this is gonna be 1 by V into the dV of it. Limits are from V initial to the V final we have kept it. So this is minus of the nRT, ln of the V. The volume it is going from the V initial to the V final. That means this is gonna be minus of the nRT, ln of the V final upon the V initial. This is gonna be the work done in this case. Okay, so minus of the nRT. Now this is the work of the expansion. That means initial volume that you are having, this is the smaller one. System it is the, let me just tell you, this I told was the of the compression we were talking, that is for just to tell you the reversible process. So this is the system. Now the system it has expanded in this case. So slowly it has expanded by removing the weights now. So you were not applying it, you were removing the weights slowly. Okay, the reversible process, this is the V initial and this is the V final. So that means work is done by the system. Work done by the system it is negative only, minus of the nRT ln of the V final upon the V initial. Option A is the right answer in this case. I hope it's clear. Okay. Now the next, this question you are having. So this begins now the questions from the June exam conducted in the year 2014. Till 2013 we are done up to that. Now the question it says the figure given below represents the path followed by a gas during the expansion from the A to B. So from point A you are going to the point B. So what is the work done in this? So PV plot has been given to us. So work done we can say total in going from A to B. You can consider a point C in between. This is the point C. So this will be equal to the work done in going from A to C plus of the work which is done in going from C to D. This is what we can do it. Now work done we know minus of the P external into the dV it is there, dV it is there. Now for the process which is A to C, if you see the volume term it is remaining to be the fixed, that is it is 1 liter only. That means work done in the AC it is gonna be 0 as dV value it is 0 in this, there is no change in this value, right? Now in for the CB and going from C to B, P external, the external pressure it is of the 1 atm. This is the external pressure which is of the 1 atm. The volume change we are going from the 1 liter to the 5 liter volume we are going. So this is gonna be minus of the 1 atm into the final volume which is 5 liters minus of the 1 liter which is there. So this becomes minus of the 4 liter atm. So in the units of the liter atm only the work done has been asked to us. So that means the answer is the minus of the 4. That means option D will be the right answer. We have just talked about the magnitude in this, but we have seen that the expansion work is being done. So work is done by the system. So that means work done is gonna be negative only. Okay. So this is the answer. Next, this question now. In a bomb calorimeter, the combustion of 0.5 grams of the compound. So what basically happens in the bomb calorimeter is you burn your fuel. Okay, and by burning the fuels, what we do is we find the calorific value of it. We find the calorific value of the fuels, value of the fuels. What is meant by the calorific values? That is, if you are burning a certain amount, suppose 1 gram of the fuel you have burned it, then how much amount of the heat it has been produced in this. So for that, this experiment it is performed in the bomb calorimeters. Okay. So we are having a zero point 0.5 grams of the compound which has the units molar mass of the 50 grams per mole. It is increased by the temperature of the 4 Kelvin. So change in the temperature that is taking place, it is by the 4 Kelvin. If the heat capacity of the calorimeter along with that material it is 2.5 kilojoules per Kelvin, the molar internal energy of the combustion in the kilojoules it is gonna be. So we know that internal energy it is as delta U, we say it is NCV into the dt of it, right? So here if I talk in terms of the N, so here what we generally consider the units you have to keep in the mind that you are asked to find the units in the kilojoules, right? So if I take the N value like this, because it is in the kilojoules, if NCV dt I'll be finding, I'll be getting in the answer in the joules per mole values. That is per mole we will be getting these answers. So what we do is to get it into the joules per mole, you take the gram, 50 grams per mole of it into the CV value, which is 2.5, that is in the kilojoules per Kelvin, into the temperature change, which is of the 4 Kelvin. So here if you see the units now, this Kelvin and per Kelvin term it is getting being cancelled out, right? And divide this with the mass, which is of the zero point 0.5 grams. So this grams and per gram term it will get cancelled out. So here you are seeing we are getting the answer, that is in the kilojoules per mole. This value we are getting in this, right? So per molar internal energy it has been asked to find it out, that is in the units of kilojoules per mole only we have to find this. Okay, this is the way that we can do it. If the other way, if you see it, that you take the zero point 0.5 and then you take it 50 grams per mole of it, from the units you can see you will be not getting it. So it is in the kilojoules per Kelvin and the per Kelvin. So this Kelvin per Kelvin will get cancelled. Gram and per gram it will get cancelled. We are getting the answer in the kilojoules and the mole term it will be there. If we take the number of the moles, that is by given weight by the molecular weight. So you can see we are not getting the correct units. So this is the incorrect method. You have to keep it in this way only so that you can get the units of kilojoules per mole. Okay, so on solving this decimal I can bring it in the denominator, and this one we can take it above. So this 10 and 10 it gets cancelled. 25 fours are it is 100, and this is 10 in this. So 100 into the 10, that means 1000 kilojoules per mole, the value of the molar internal energy we are gonna get is this. Now the heat is given by the system, so this is gonna be minus of the 1000 kilojoules per mole. That is because heat is given during the combustion. During the combustion. Okay, that means minus of the 1000 it will be there. So option B it will be the right answer in this case. Okay, next. For a process in a closed system, the temperature value it is equal to. Okay, so again using the Maxwell's square we can do this. So good people have studied under very amazing teachers. Right. So now we know that du value that you have, it is equal to TdS minus of the P dV of it. So if you talk about this at constant volume, so del U by the del S at the constant of volume, this is equal to your temperature only. So this is what we are having. But you can see in terms of the internal energy, none of the options that has been given to us. Right. So now one more way we can write the enthalpy now expression, which is V dT plus of the TdS. This is the expression that we have, because dH you can see it is dependent upon the entropy and the pressure. So dAP and the dS term it will be there. In front of the pressure there is the volume term. Arrow is going towards it. So positive value it is there, and the dS value we have taken opposite of it is the temperature. So plus of the TdS. Right. If I talk it at the constant of the pressure. So del H by the del S at the constant of the pressure, this is gonna be equal to the temperature. Okay, so these are the two expressions that give us the value of the temperature. So del H by the del S at the constant of pressure, option B will be the right answer. Okay, next this question now, the exact differential f of a state function which is function of the x and y among the following is. So that is again the exact differential is going to exist for the state functions. That means here the Euler's theorem we have to see again. Euler's theorem, it has to be stated according to which if z you are having, which is function of the x and the y, so dz it is written as m dx plus of the n into the dy of it. So this condition it should be satisfied that del m by the del of the y at the constant of x, this is equal to del n upon the del of the x at the constant of the y. This condition it should be satisfied. Now from the given options, if I see here it is x dy only. So that means that term with along with the n only it has been given. The n value we are not having. So that means in this we cannot apply the Euler's theorem. So that is not gonna be there. The second option, if you see, it is dx minus of the x by dy into the dy of it. So m value it is 1 in this case. So del m by the del of the y we have to do it at the constant of the x. Instead of the m now you are having this 1 value. So a constant value it is there, that means it is gonna be equal to the 0 only. So again you are seeing that Euler's theorem is not being satisfied in this. Next, the option C, if I see, here only I am doing it. It is saying it is y dx minus of the x dy of it. So it becomes del by the del of the y, of the differentiation of the y. This is at constant of x. This should be equal to minus of the del x by the del of the x. This is equal to the y in this. So this we are getting the 1. This we are getting as minus of 1. Both of them they are not equal. That means C is also not gonna give me the exact. This condition is not being satisfied. Now the option D, it will be the obvious answer because A, B, C we have already eliminated. But let us check it for this one also. It is 1 by the y dx minus of the x upon the y square into the dy of it. So it will be del of the 1 by y with the del y at the constant of the x. This is equal to minus of the del by the del x of the x upon the y square. This is at the constant of the y. This differentiation is being done. So on solving this, we will be getting minus of the 1 by the y square. This is equal to now minus of the del by del x of the x upon the y square. Again, the answer is minus of the 1 by y square. So left hand side is being equated to the right hand side, which means the conditions of the Euler's theorem is being satisfied in this. Okay, next this question now. Given the following two relations, x1 into the d mu1 plus of the x2 into the d mu2 is 0, and in terms of the volume also it has been given. For a binary liquid mixture at constant temperature and at constant pressure, the true statement is. So this is from the Gibbs-Duhem equation only. Gibbs-Duhem equation, which describes that what is gonna be the change in if you are adding a certain component, that is n1 number of the moles of the ith component you have added. So what is the change in the chemical potential? So like this we write it n1 into the d mu1 plus the n2 into the d mu2. This is equal to the 0. This is how we used to write it. So if in the terms of the number of the moles that we are writing it, we can write it in terms of the mole fraction also, because they both have been just divided with the total number of the moles in this. So if I divide this with the n1 plus the n2, here also if I divide it with this sum, there is gonna be no difference in this. We will be getting x1 into the d mu1 plus the x2 into the d mu2, which is equal to the 0. That means this expression is the true one. Now the second one which is given here, also this mole fraction has been given. Now here instead of the chemical potential, molar volumes have been given. So chemical potential was also nothing new to us. It was just a change in the Gibbs free energy that we were having. If the ith component it is added to it, that was at constant temperature and pressure. Now in the terms of the volume also, if you see this expression, you are able to write it. Let me give you a proof for this. Where the volume, if you see, it is function of the temperature, pressure, and the to binary liquid it is there. So that means number of the moles you can consider n1 and the n2 in this. Right. So exact differential of the dV, if I see, because it is your state function. So dV it will be equal to a del V by the del T into the dt. This is at constant pressure, the number of the moles N1 and the N2 plus of the del V by the del T del V by the del P into the dt, keeping the temperature, number of the moles 1 and the number of the moles N2 to be the constant, plus of the del V by the del of the N1, keeping the temperature, pressure and the N2 to be the constant, plus of the del V by the del of the N2. This is at the constant temperature, pressure and the number of the moles which is N1. So this values which is del V by the del N1 which is describing the change in the volume with the addition of the N1 components in this. This is nothing but the molar volume V1 only, and this is nothing, it is the molar volume V2 only. So like this we can write it. Now we are talking at the terms of constant temperature and the pressure, which means dt value it is 0 and the dp value it is 0. This is at the constant temperature and the pressure. So from this, using this conditions, we are getting that my dV value, this is equal to molar volume V1 into the d of the N1 plus of the. This is what you are getting, this dN1 and the dN2 it was present, plus of the V2 bar into the d of the N2 of this. Right. So now we know that volume V, it is gonna be summation of N1 into the V1 or the Ni into the Vith component. Now here two values are only there, so this is gonna be N1 V1 plus the N2 V2 of it. N2 V2 of it, right? So now the complete differential for the dV, it is gonna be N1 dV1 plus of the V1 into the d of the N1 plus of the N2 into the d of the V2 plus of the V2 into the d of the N2 of it. And like this we can write it. Now both these expressions 1 and 2, they are of the exact differentials only. So both of this it will be equal. So here the molar volumes you will be having, both of this that will be equal. Only the conditions if the N1 dV1 plus the N2 dV2, this is gonna be equal to the 0, right? And also these are the molar volumes only, right? So this conditions it will be satisfied. You can divide it with the, in terms of the moles, if you have to go it, N1 plus the N2 into the dV1 bar plus the N2 upon the N1 plus the N2 into the dV2 bar. This is equal to the 0. LCM is the same. It will go on the other side. So this becomes the mole fraction x1 into the dV1 bar plus the x2 into the dV2 bar. This is equal to the 0 only. Right? So like this also we could write it. So you are seeing that this condition is also being satisfied as per the Gibbs-Duhem equation. So both these relationships that are given, A and B, they are the correct. Okay. So option A, it becomes the right answer in this, which states that both these relations are the correct ones. Okay. Next, this question now. Now this begins the questions from the CSR exam conducted in the December month of the year 2014. The question it says at the high pressure, the fugacity coefficient of a real gas is greater than the one. So fugacity coefficient that you have, fugacity coefficient, this is nothing. The ratio, this is denoted with the phi. This is equal to the relationship which is fugacity upon the pressure. Fugacity is nothing, it is pressure of the real gas. Pressure of the real gas. And P is the pressure that is for the ideal gas. Pressure of the ideal gas. This is what we say. Now it is at the high pressure, they are saying this fugacity coefficient it is greater than the 1. That means phi is greater than the 1, or if by the P it is greater than the 1, or the pressure of the real gas that you are having it is more than that of the pressure which is of the ideal gas. Right? So pressure is produced when the particles they are colliding with the one another and also with the walls of the container, right? So that means in this case, in the real gases, What term has dominated? That is why they are producing the high pressure. That means the repulsion, it is gonna be dominating. Repulsion, it dominates the attraction. That is why only they are producing the large amount of the pressure on the walls of the container. And so clearly it says that the repulsive term it overweighs the attractive term, option B, which is saying this thing as the true. I hope the concept is clear. Now moving to the next one, this question. The heat capacity of the species, it is independent of the temperature if it is which type of the gas. So now the heat capacity we have been asked to find it out. So we know about the degrees of the freedom. Degrees of the freedom, that we say the total number of the ways in which the particles can distribute their energies. Right? So total degrees of freedom we have, that is 3n, where n is the atomicity. N is the atomicity. This is what we say. So now out of these 3n, we have different degrees of freedom. We have the translational degrees of freedom, we have the rotational degrees of freedom, and we have the vibrational degrees of freedom. Okay, based upon the atomicity of the gases, these number of degrees of freedom it is gonna be varied, right? So now the temperature dependence out of these degrees of freedom, it can be seen only for the vibrational degrees of freedom. This is dependent on the temperature. Its contribution is seen only when the temperature is high in them. Okay, if I talk about the monatomic gases firstly, the monoatomic, that means n value in this it is gonna be 1 only. So total degrees of freedom we are having, that is 3 only. So these 3 degrees of freedom that you have, they are gonna be translational degrees of freedom only. That means no contribution of the vibrational or the rotational degrees of freedom we are having, right? Whereas if you talk about the diatomic gas, the diatomic. In this n value it is 2. That means total degrees of freedom it is gonna be 6. Out of these 6, the translational degrees of freedom we have, that is 3. The vibrational you have, that is 3 and minus of the 5 will be there, and the rotational one you have, that is 2. So this is gonna be 1. This vibrational degrees of freedom, you can see the contribution it is starting in the diatomic gases. So here the dependency it will be there on the temperature, whereas for the monatomic gases, no vibrational degrees of freedom we are having, that means no dependency on the temperature. So it is in the monoatomic gases that there is not gonna be that the heat capacity that we will be having, it is independent of the temperature. Okay, next this question now. A thermodynamic equation of states that relates the chemical potential to the composition of a mixture is known as, so we have seen it as N1 d mu1 plus the N2 d mu2. This is equal to the 0. This is nothing, it is my Gibbs Buchan equation. So mu is the chemical potential and the composition, which is the number of the moles, which implies option B will be the right answer in this. Okay, next this one now, the temperature dependence of the electrochemical cell potential. That means del E value you have to see, the variation with the temperature you have to see it at the constant of the pressure. Now we know that dg value that you have, it is vdp minus of the sdt. Again from the Maxwell square only this expression it has been obtained. Now if I'm talking at the constant pressure, if we are talking, so in that case dp value it will be 0, dp will be 0, which means dg is minus of the s into the dt of it, or we can say del g by the del t. At the constant of the pressure it is minus of the s. In terms of the change if we are talking, so del of the delta g by the del t, at the constant of pressure it is minus of the delta s of it, right? Now del g we know, delta G it is minus of the NF of the E cell, because we are talking for the electrochemical cell potential. So delta G it can be related to that. So it will comes del by del T of the minus of the NF of the E cell, that is at the constant of the pressure. This is equal to minus of the delta S of it. So now N and the F, they are the constant. N is number of the electrons involved in the reaction, and the F, it is your Faraday's constant. Faraday's constant, so it will be coming out of this. So minus of the NF of the del E upon the del T at the constant of pressure, it is minus of the delta S of it. So negative signs on both the sides, that will get cancelled out. So del E by the del T at the constant of the pressure, this is equal to delta S upon the NF. So this is the temperature dependence of the electrochemical cell potential, which implies delta S upon the NF. Option C is the right answer in this. Okay. Next, this question now. The value of the delta U minus of the delta H for the reaction. So again, the reaction we are having. So delta H, it is equal to delta U plus of the delta Mg RT. This expression we are having. So now we are asked to find the value of delta U minus delta H. Make sure you are reading these statements very, very carefully. Don't make mistake in this, because both these options you will be getting, that is for delta H minus delta U and delta U minus delta H also you will be getting. So read the statements carefully. Okay. So delta U minus of the delta H, it is minus of the delta Mg into the RT of it. This is what we are getting, right? So now delta Mg, if I see change in the number of the gaseous moles of the product side, on the product side I'm having 3 gaseous moles, okay, minus of the 3. Now on the reactant side you are seeing 0 gaseous moles that is present, so it will become minus of the 3 RT. So that means delta U minus delta H, it is minus of the 3 RT. Okay, so answer is the option A in this case. So you can see plus term is also given to us. If I would have not read the statement carefully, I would have thought that previously also it was delta H minus delta U only was asked to us. Then the plus 3RT I will mark, and that will give me a negative marking. So it is delta U minus delta H that is asked. So negative sign, it plays a very important role in this case. Okay, next, this one. If the pressure of the system it is greater than the pressure of the surrounding. So this is the beaker, suppose you are having. In this there are some of the gaseous moles which are present, and this is the piston that we have applied in this, right? So now the pressure is being created by the gaseous molecules, which is the pressure of the system. It is there, pressure of the system. Now some pressure by small pebbles, suppose reversibly we are doing it, and this is gonna be the pressure which is of the surroundings, right? Now the condition is pressure of the system it is greater. So pressure of the system, it is greater than the pressure of the surrounding, which means the more of the pressure is applied by these gaseous molecules, so work is done by the system, right? Because piston, it will start moving in the upward direction. So work is done by the system, by the system on the surroundings, on the surrounding. This condition that will be there. The statement that says work is done on the system by the surrounding, incorrect. Second one, it says work is done on the surroundings by the system. This statement is the true. Okay, so B is the right answer in this case. Next, delta H for a reaction is equal to the slope of which of the following plots? We know that delta G, it is equal to delta H minus of the T delta S of it, right? So if I divide this with the temperature, divide it with the temperature, so we will be getting delta G by the T. It is delta H upon the T minus of the delta S of it. So if you make a plot for delta G by the T versus 1 by T, so Y is equal to the mx plus of Pc. So slope value you wanted, that is delta H in this case, right? So that is the plot we are making for the del G by the T versus the 1 by the T. So this is giving me the value, that means del G by the T versus 1 by T. Option B is the right answer, which is giving me the slope of the delta H in this case. Okay. Next, this question, a reversible expansion of 1 mole of the ideal gas. It is carried out from 1 liters to the 4 liters under the isothermal conditions at 300 kelvins. What is delta G for the process? Okay, so we know that dG value, it is equal to VdP minus of the S dt of it. Right now the condition is isothermal. Isothermal, which means dt value, it's gonna be equal to the 0 in this. So we can say that dg, it is equal to the vdp of it, right? So now for the ideal gas it is given. So for the ideal gas, PV is equal to the nRT. So 1 mole it is given. So RT it is there. So volume is gonna be RT upon the P of it. This you can substitute in your expression. So dg will be equal to RT upon the P into the dP of it, right? So integrate on both the sides. Integrating. So we will be getting dg. This is equal to RT upon the P into the dP. This becomes delta G, that is equal to RT ln of the P, right? Pressure, it is going from the P1 to the P2. So it will become ln of the P2 upon the P1 of it, right? This is what we are getting, that is in terms of the pressure we have got it. Now the condition is isothermal. For the isothermal conditions, we have P1 V1 equal to the P2 V2 of it, right? So here P2 upon the P1, this is gonna be equal to V1 upon the V2 of it, right? So that means delta G in terms of the volume if I see, that is gonna be RT ln of the V1 by the V2, or this is RT ln of the P2 upon the RT ln of the P2 upon the P1 of it. Right now from the given conditions here you see volume change has been given to us. So volume expressions we are gonna use. Temperature is also given and the volume from the 1 to the 4 it is given. So V1 it is 1 liter and V2 it is 4 liters. So delta G, this is gonna be RT ln of the V1 by the V2 of it. So 300 into the R into the ln of 1 by 4 it will be there, right? So R value they have kept it as it is. So this is going in the numerator. So minus of the 300 into the R ln of the 4, or we can write it as minus of 300 into the 2 R ln of the 2. Because this 4 we can write it as 2 square. So that 2 we have got in the front. So it will become minus of the 600 R into the ln of the 2. So this is gonna be your answer, right? So minus of the 600 R into the ln of the 2. So option C will be the right answer. Again, you are seeing for the positive term, it also has been given to us. So if I am not looking at the units carefully and considering that pressure term only it is there, P2 by P1 I will be considering. That is instead of volume, if I take the pressure terms, then the positive answer we will be getting. So make sure again and again I am saying statement reading is very very important for us. Okay. Now the next discussion we are having, the temperature dependence for of the vapor pressure of the solid A. It can be represented by this expression and that of the liquid A. So solid A you are having solid A, which is giving, which is having the log of the P value, it is 10 minus of the 1800 upon the T, and for the liquid A it is there, which is having the log P equal to the 8 minus of the 1400 upon the T value it is given to us. So now the temperature of the triple point of the E. So triple point is the temperature at which all the phases which is solid, liquid and the gases they coexist. So the temperature at which the solid, liquid and the gases they coexist in this. That means log T for the solid and for the liquid it will be equal. That means 10 minus of the 1800 upon the T. This is equal to 8 minus of the 1400 upon the T. That implies that will become 2 is equal to 400 upon the T. So temperature we are getting from here, that is gonna be 200 Kelvin. So triple point of the of the A, it is 200 Kelvin, that is the temperature at which all these three, that is solid, liquid and the gases, they will be coexisting. Okay. Next discussion, the non-spontaneous processes among the following. So again I told spontaneous and the non-spontaneous difference is that spontaneous processes they continue on their own once the initiation has been provided to them, and the non-spontaneous processes it will be continuing unless and until the force is being applied over them. Right, that means external help we are giving them. So the first one it is saying vaporization of a superheated water at 105 degrees centigrade and at 1 atmospheric pressure. So vaporization, it means liquid is converting into the vapor phase. So water it is there, water boiling point it is 100 degrees centigrade. Now already the temperature we have made to be at 105 degrees centigrade. So that means initiation we have already provided in this case, right? That means this process is gonna be spontaneous. So it will continue all the liquid, it will continue till all the liquid is converted into the vapor. So this is your spontaneous process. Okay. Next is expansion of the gas into the vacuum freezing. The vacuum it means that is no external force it is acting on this. So expansion of the gas, that means it is expanding. Work is being done by the gaseous system. So it will continue on its own because no external force is applying over it. It is in the vacuum condition. Again, the process it is gonna be spontaneous in this, right? The next one, freezing of the supercooled water at minus of the 10 degrees centigrade and at the 1 atmospheric pressure. Again, you see, now freezing is being done. That means liquid is converting into the solid. So that water it is given. So water it freezes at 0 degrees centigrade. Now we have made the temperature below it. So that means initiation we have provided in this case. So again, this process it is gonna be spontaneous only. Okay. Next, freezing of the water. It is at 0 degrees centigrade and at 1 atmospheric pressure. So now the freezing is done at a different temperature, which is liquid is converting into the solid, but this is gonna be in the equilibrium because it is at 0 degrees centigrade and at the 1 atmospheric pressure. Only the phase transition it will be taking place. This is the phase transition that is taking place. So here equilibrium it is present. That means the rate of forward reaction it is equal to the rate of backward reaction. It is not gonna be the spontaneous process, right? Because it is the equilibrium it is there, it is non-spontaneous. That means in a particular direction the reaction it is not continuing on its way, right? So we were to choose the non-spontaneous only. So option D is the right answer in this case. Okay. So this was the last question that was to be discussed in this part. I hope all these questions they are clear to you. So till the December exam, that is of the year 2015, the questions we have done it. Now the remaining questions which is from the June 2016 to the year that is the 2025, that we will be discussing in the next. I hope all these questions that we have discussed in this part they are clear to you. If you still have doubted any of the questions, that you can ask me in the comment section. I'll surely reply to that. Thank you so much for watching. And if you have understood the concepts, then make sure you like the video and do share it with your friends as well. And if you have not subscribed to the channel so far, then do subscribe to the channel also so that you can get notifications for the upcoming parts. Okay. Thank you so much for this one. I'll be meeting you in the new video now.